Well, it's been a while since I recorded a video, but these worksheets are a little bit updated, so that date's not accurate. So it's time I shot a new video for this, or the first video for this one, really, I suppose. So this is building off of what we've done in class. Iron nail, conductor, neutral plastic rod, insulator, nowhere near any excess charge sources. So that means there's no polarization going on yet. So what we learned was insulators, the charge, the electrons, these represent atoms. They are confined, the electrons are confined to stay within the cloud or space of the atoms. They are not allowed to move throughout an insulator. It's why it does not conduct electricity. The electrons stay stuck in the structure. So I draw a little positive sign to represent the protons. The circle represents the atom or the molecule, depending on what we're talking about here. Then I put electrons in here, and the electrons are kind of scattered. They're arranged in the crystalline structure of the molecules, and they are fixed, and overall the object's neutral and not polarized. All right, so the circles are kind of a boundary in which charge, whatever's in there, can't move out. Now metals are different. In metals, the valence electrons are allowed to move, and they form the Fermi sea of electrons. So if I draw similar atoms making up this nail, right? There they are. This one's a little small. I still have the positive, the nucleus of the metal. That's positive. And within that circle, there are some electrons, right? So what that circle in a metal is, it's the nucleus, which might have 8 protons, 8 neutrons. And then there's the electrons that satisfy complete orbitals. But the valence electrons we draw outside of that circle. So I'm just pretending it's like 1 valence electron per atom here. They're allowed to move anywhere throughout the conductor. So this electron is absolutely indistinguishable from this electron. This electron's bouncing around and could be moving anywhere in that metal, kind of like a gas in air. All right. So when we take those and we put them near something, for instance, a positively charged Van de Graaff generator, so these plus signs are representing the fact that there's excess charge on the surface of this Van de Graaff. All right, what happens is the two objects get polarized. Now, the rod, the electrons they have to stay within these circles. So what happens is the electrons all get pulled to the right side of their molecules. So this is called polarization. Polarization. Look, at the end, this side's negative. At the end, this side's positive. So it's polarized. There's a little more negative charge to the right side, a little more positive charge to the left side. It's polarized. The nail, however, something a little more interesting happens. Right? The electrons can move further. Right? They get pulled towards the Van de Graaff. Now, there's a balance here because those electrons also repel each other. So what happens is you get a buildup on the surface. Over here, I've drawn too many, and it kind of fades out across the nail. So you get much more polarization. And I didn't do a good job. I drew too many. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, and I drew too many electrons. So I probably should reduce the number there. But you get the idea. What happens is this side's positive, this side's negative. Positive, negative. Same thing over here, but it's negative, positive. They're polarized. Polarized by what we call an external charge source. All right, the Van de Graaff in this case is an external charge source that influences the space around it. It's going to repel anything positive, attract anything negative. All right, now over to our experiments. We've got our positive Van de Graaff generator. All right, we've got our neutral conducting pie pan. All right, if you have something neutral, if you have something neutral and touch it to something positive, what happens is this positive is attracting electrons. All this big positive Van de Graaff generator, right? There's a pull on electrons. So this pie pan has, just like the nail on the first page, has a bunch of electrons in it, right? The valence electrons. So what actually happens is some of those valence electrons actually stream off of the plate onto the Van de Graaff. So let's say these 4 electrons stream off onto the Van de Graaff, right? This ends up being charged positively, right? So electrons, when it touches the positively charged Van de Graaff, they get drawn off of this plate. Not all of the electrons, right? Not even all of the valence electrons. Some of the valence electrons. And as long as you take some electrons away, that leaves the plate being positive. And the electrons that are remaining, they spread out, right? They can't totally cancel out the positive charge, so now this thing's nice and uniformly charged positively. Now, if we take that pie pan, right, and we touch it to another pie pan, it's basically this experiment again, right? And what happens is some of the electrons move over here. They get pulled over here, right? This one's positive. This one's neutral. Electrons are on here are going to get drawn towards the more positive thing. So maybe 2 electrons jump over there, or 2 units of charge jump over there. And we end up with +2 and +2. This is neutral to start off, but then it loses some of its electrons over to that pan. So whenever you have something neutral, if you touch it to something charged, there's going to be a swapping of charge. All right? By what method did the uncharged pie pan gain charge? Conduction. So conduction, there was conduction. Electrons flowed from one to the other via their contact. All right? 2 pie pans touched together, but not near but not touching a positive Van de Graaff generator. So we got our positive outside charge source here. It's going to try to pull electrons towards it. So this side of the dome ends up getting charged negative. This side, these electrons that accumulate on here are getting pulled. Some, these ones maybe were started off in the plate. Maybe these ones here started off over here. So whatever one's moved over to here, it leaves behind the opposite. All right? And in the middle, it's fairly neutral, right? So maybe you can kind of picture this. The electrons get pulled over to one side because it's a conductor. There's what we would call a back pressure. These electrons are repelling each other, right? They're trying to stay away from each other, but they're all getting pulled to the left. And then when you separate them, the charge can kind of relax. The charge relaxes and spreads out, and we get a more even distribution. We get a more even distribution over here now. So we got negative, positive. You separate them. When you separate them, this one had more electrons. It had electrons that had come off of this one, so this one's now positive. All right. This one here's the tricky one. Kids had a lot of trouble kind of picturing this. And this is a difficult topic to try to teach because we're teaching about something you can't see. You can see the tinsel move when we do the electroscope experience, but you can't see the electrons move. We have to kind of, I don't want to say believe, but we sort of do. So what happens is when you bring this over here, it polarizes. This side becomes negative. That's step one. All right. So this side of the pie pan's positive, this side of the pie pan's negative because it's been polarized. Now when you ground it, right? When you ground it, what you're doing is you're opening up a pathway for more electrons to flow either onto this plate or away from this plate. So this is still really positive. All right, basically by grounding it, I've made this pie pan infinitely big. Infinitely big. So what happens now is, yeah, those ones are still over here. But because I've attached even more metal to this, it draws even more electrons onto it, right? So it's polarized, but then all of a sudden, I touch it to this, now the Van der Graaf can actually pull electrons, not only just across the plate, but actually can draw electrons up from the ground. You get more flowage up here. You get maybe, let's say you deposit, what do we got there? 8 more on there. And when you disconnect it now, well, there were 8 more electrons than protons on there. So our charge now becomes 8. It's called induction. Polarization. And then grounding. And we take it away from the area because the electrons got sucked up on here due to the Van der Graaf. The Van der Graaf's pulling on them through the air, right from the ground, right up onto here. When you ground it, that's what you're doing. More electrons can come onto that. And when you remove it from the area, and it's all because of this external force, right? If you just have a pie pan without an external force and you ground it, nothing happens. Nothing happens. Electrons, if it's charged and you ground it away from a Van der Graaf, yeah, charge is going to flow, either to make it neutral. But without this external force coming from here, it wouldn't draw more electrons up onto this plate. So then you move away from the you remove the nail quickly. You got 8 extra electrons on here. So then when you move away from the Van der Graaf generator, it still has those 8 extra electrons, so it's charged negatively now. Now this one we talked about, this gets charged up very negatively when the lightning strike hits. Lots of negative charge on there, right? Mike pie pan is neutral. So kind of, I'll draw a couple steps out here, and I'm gonna simplify Mike pie pan. 1, we'll draw step 2 here. This is ground, right? So this is neutral right now. It's ground. It can take in or give electrons if they're needed. A Mike pie pan, when that strikes, there's Mike pie pan. I'm just going to draw him as a ball. Mike pie pan gets polarized. All right, Mike pie pan gets polarized. The electrons get pushed over to this side. And since it's polarized now, this is going to attract. This side of the Mike pie pan is more positive and it's closer to the big negative charge. So there's a force imbalance here. This side's getting pulled more than the left side is being repelled. The left side's being repelled from this. The right side's being attracted. But because the right side's closer, this force is stronger. So the right side gets attracted. Well, when it gets over there and hits, right? It gets over there and hits. This big negative thing transfers charge. When it hits, I guess I should have made it touching it. This is getting to be a bad drawing. Some electrons flow onto it. The positive side of the battery pulls electrons. All right? Now he's charged negatively, so he's immediately going to repel away from the negative side over here. So this stays negative the whole time. Mike's pretty small compared to how much charge is on that thing. So it repels, it hits this, electrons flow off into the ground, and it is neutral again. And the whole thing whole thing becomes neutral when grounded, right? So the whole thing starts over again. We end up cycling back to here. Neutral like pie pan, swings back, gets polarized, hits this, picks up more charge, repels, goes back, hits this, deposits charge into ground, becomes neutral, swings back, gets attracted, it just keeps going.